Yeah, so welcome back, everybody. Uh, so let me quickly recap what I had covered in the last part. That is part three of these lectures on Lovasz theta function, STPs, and algorithms. So I had introduced the notion of a semi-definite program, which henceforth through this lecture I'm going to call an SDP for short, okay? Which was basically an optimization problem where the variables of the optimization problem, which typically look something like max f of x such that some g1 of x greater than 0, g2 of x greater than 0, f g1, g2 in general can be arbitrary functions in an arbitrary in a problem, and x is a set of variables. But for a specific case of a semi-definite program, the variables have more structure. They come from this matrix capital X. Okay, they come from this matrix capital X, whose entries xij are the actual variables appearing in the optimization. Okay, the matrix itself is symmetric and positive semi-definite, right? And the objectives and the constraints are linear in the entries of the matrix. So these F's and G's will be linear in the entries of the matrix. Okay, so that's how we had set up what a semi-definite optimization problem is, and we called it a semi-definite program. Okay. The second thing we had seen is that theta of g, which is the theta function of the graph of our input graph g, can be expressed as a minimization SDP. Okay, that is the object you want to minimize. Here I've written maximum, but it can be written as minimization of a linear function of these variables xij subject to certain constraints. Okay. And the point is that semi-definite programs can be solved efficiently with some technical conditions, but yeah, for our purposes, we can assume that it can be solved efficiently, which means that given an input graph G, I can actually determine what theta of G is. Okay, so that's one computational aspect. But on the other side, it allowed us to prove the sandwich theorem, so-called, which was proven by Lovasz, which is basically that theta of G is sandwiched between, I should be careful here, this should be, yeah, the clique number of G complement and the chromatic number of G complement. So theta of G is a function of the graph that lies sandwiched between the two. And the way that we had shown this was using the semi-definite programming formulation. Okay, by showing that you can extract out a feasible solution for the semi-definite program from a vector, from a k coloring of the complement graph. Okay. So this summarizes what we had discussed in the previous one. Now, there are some follow-ups to this that I should do justice to and discuss at least shortly. So certain classes of graphs I'm going to mention, but the focus of the rest of this lecture is primarily going to be on the influence that this relaxation that Lovasz proposed has had on the algorithms community. So for instance, there's huge amount of work inspired initially by this Lovasz work, implicitly at least, that gives more and more efficient algorithms for certain problems. Okay, in particular, we'll discuss one such thing with the max cut problem, and the solution to that will also be based on a semi-definite program. Okay, so before I go to the algorithm side of it, a bit more on the structural side. Okay, so there are these classes of perfect graphs. So notice that the sandwich theorem, let me write it here, stated that for all graphs G, I had the clique number of G complement was less than equal to the theta function of G, which was less than equal to the chromatic number of G complement. Okay, so this was the theorem that we had shown in the previous part, Lovasz sandwich theorem. Okay. Now, perfect graphs are a specific class of graphs where the clique number of the graph, or let me say of the, clique number of any vertex-induced subgraph, I should say. Okay, for any vertex-induced subgraph G prime of G, the clique number and the chromatic number, they kind of they match up. Okay, what we know trivially is that the clique number is at most the chromatic number, Okay, because if you have a clique, then you need at least that many colors to do a proper coloring of it. But here what it says that actually turns out to be equal on all induced subgraphs also. Such graphs are called perfect graphs. Okay, they were initially defined by Burge in the 1960s, I think. And what you can see is that you can compute um, the clique number and the chromatic number efficiently for all perfect graphs. Okay, although for general graphs, I had mentioned that this is a really hard problem computationally, but we can compute this efficiently because they match up. That means both of their values should be equal to theta of g. Okay, and once they become equal to theta of g, what do I know about the theta function? That given an input graph, or theta of g bar, I should say, I flip the g and complement. So what do I know about theta of g of any graph? I can actually compute it by, taking the input, feeding it into a semi-definite programming solver and get the answer, right? So that's why this is true, that we can compute it efficiently. And examples of perfect graphs are bipartite graphs, chordal graphs, and interval graphs, which are commonly known classes of graphs. Okay. So perfect graphs have got one good thing, that is you can compute these quantities, which are typically hard to compute on other graphs. On perfect graphs, you can compute it efficiently. Okay. There are also a couple of very nice theorems. Lovasz showed in 1972 that G is perfect if and only if its complement is perfect. Okay, so what does that mean? That means on perfect graphs, you can compute all these quantities. You can compute the chromatic number, you can compute the independence number, you can compute the clique number, all of these, simply by computing the theta function on either the graph or its complement. Okay. And the strong perfect graphs theorem, which was proved in only 2006, actually characterizes this. Okay. That a graph is perfect if and only if it contains no odd hole and no odd antihole. Okay. So it gives a structural characterization of perfect graphs. Okay, what does a odd hole mean? It's an odd induced cycle of length at least 5. That is the graph. Sorry, should be odd. So maybe the graph has a cycle of, say, something like C7 sitting in it, and the other edges are, of course, there. And there may be many more vertices in the graph. But if it has a hole of this form, if it does not contain any hole of this form, only then it is perfect. So the smallest imperfect graph, so called, say the smallest graph that is not perfect is actually C5. Okay. And we have seen that C5 also has some other significance, as you've seen for the theta function. Okay, good. So that's all that I wanted to cover about perfect graphs. There are certain other results, but I won't have time to get into them. Okay, like what's the gap between theta of the graph and and the independent set size for non-perfect graphs. Okay, so what kind of gaps can be there? All of that. So I will not get into that over here. So now let's go on to the main topic of this part that I want to focus on, which is on semi-definite programs and how they're used to design algorithms for problems. So let me again go over what we call as computers in computer science as easy and hard problems. Okay. So easy problems are those for which there are efficient polynomial time algorithms. Okay. So what do I mean by efficient? It basically means that you can give an algorithm which given an input gives the desired output and runs in time polynomial in the size of the input. Say maybe order n squared time, where n is the input size, or order n cubed time or something similar. So typically algorithms will be n squared, n cubed, n to the power 4. We typically don't have algorithms that run in n to the 100 or something. That would be quite unnatural. So here are some examples, and some of this you might have already seen. For instance, if you want to sort n numbers, if you want to find a matching in a graph, you want to find a minimum spanning tree in a graph, Or I guess you might have seen this in the previous lecture also, finding a min cut or a max flow in the graph. So all of these are easy problems. That is, it doesn't mean the algorithms to find them are easy. In fact, they may be quite involved and very clever. But the problems are easy as in there is an algorithm that solves them in polynomial time. Okay. Yeah. On the other hand, you have these hard problems. By hard, I mean computationally hard. And these are problems on which computer scientists believe that you cannot find optimal solutions if you likely cannot find optimal solutions efficiently. Okay, unless something like P equal to NP occurs. So examples of this from minimum vertex cover, maximum cut, minimum set cover, and maximum independent set we have already seen. Okay. So I will illustrate the use of an approximation algorithm, but I will define it and illustrate the use using minimum set cover. And then we will see a very interesting algorithm for the maximum cut problem. Okay, both of these problems I'm going to define and go over. Okay. Okay, good. So now you have all of these hard problems for which we likely cannot find the optimal solution efficiently. Right? So what do we do? Do we give up? Well, they occur a lot in practice. So we should at least try our hand at it. What do I mean by try our hand? Well, maybe we don't find the exact optimal solution, but possibly in many cases, you're okay with finding an approximately optimal solution. Okay. So what do I mean by this approximate? So take an example, right? Uh, Take an input graph G. I want to output an independent set S of maximum size. So that's the objective. Right? So I cannot do this, I hope to do this exactly unless P equal to NP. So what I instead do is find a beta approximation to it. So what is the beta approximation? If I denote OPT as the optimal value or the optimal maximum set size, that can be maximum size of an independent set in the graph, that is basically alpha of G. Then I want to output an answer, S, with the guarantee that its size is at least some beta times the optimal. Okay, so beta is typically less than 1, right? So suppose maybe your application or your problem that you're looking at is fine if you find an independent set that provably, you can prove mathematically that the output of the algorithm is an independent set of size at least half of the optimal, okay, or half of alpha of G. It doesn't just apply to independent set size. For any other maximization problem, for instance, if you denote, and this standard notation in the algorithms community, if ALG is a solution given by the algorithm, we want the provable guarantee. We demand that the algorithm should satisfy that the ALG is greater than equal to beta times opt. Okay, we call it ALG is greater than equal to beta times optimal. Okay, so that's what this says. Okay, so for instance, maybe you have a half approximation algorithm for independent set, which would mean the size of the set that the algorithm outputs would at least be half the optimal set size. Okay. Now, if you consider minimization problems, which is the other thing, what would we want? Well, we don't want the size of the solution or the value of the solution output by the algorithm to be too much small, we want to minimize, so we don't want it to be too much larger than the optimal. You want to find a cover of minimum size in the graph? Well, I will not give you the actual minimum size cover, but I'll give you a cover that is less than twice of the minimum size cover within a factor 2 of it. Okay, so here the factor delta, it flips to be greater than 1 just because it's a minimization problem. Okay, so we'll see an example of one minimization problem, the vertex cover, and one maximization problem, max cut. Okay. But now at this point, you should be thinking, well, these are hard problems to compute. So how do these schemes, how can they possibly work? For instance, how can you guarantee in a maximization problem, how can you mathematically provably guarantee that your algorithm is going to output something within a factor beta of something that you don't know of the optimal, which you cannot hope to ever compute efficiently? But my algorithm is efficient. So how do you show that it's within a factor beta of some unknown optimal value, right? Well, the idea is to use a proxy to get an idea of what opt should be like. Okay. And compare your algorithm's answer to the proxy answer. Okay. And now this should give you an idea that's very similar to the Lovasz theta function. Lovasz was unable, said that, well, okay, analyzing the Shannon capacity directly is difficult. So here is something else that I can, the theta function, he devises, and he says that here's a function that's much more easier to handle, and it bounds the Shannon capacity, and let me try to analyze this instead. And this is the spirit of the proxies used here also. Okay. And to come back to the example that I stated, you want to find the height of the criminal, right? And then what do you do? Well, I can't hope to know exactly what the height of the criminal is. He's nowhere to be found. So the detective looks at the footsteps and says, well, looking at the footsteps, he can't be taller than this. Okay. So things like that. So any questions about the general framework that we are working in? So just okay, good. So let me move on to an example. Okay, this is the first approximation problem that I'm going to discuss. Okay, so for example, it's called the minimum vertex cover problem. Many of you may be familiar with the subject of vertex cover. It is a subset of vertices in a graph that touches all the edges. Okay, so here's a graph G1, right? And here are three vertices that if you choose them as your subset S, every other edge has at least one endpoint incident on one of these vertices. Okay. You'll find that every edge is incident on one of these. A trivial vertex cover for the graph is to just output all the vertices, right? Then it will be true. But our goal is not to do such an inefficient solution. Let's do a more efficient solution. Our goal is to find a minimum size vertex cover in the input graph. Okay, by efficient, I mean size of the vertex. So I want to find a subset of vertices of minimum size which all the edges touch. So for instance, for either of these graphs, these are not the minimum vertex cover, right? So the actual minimum vertex cover here for this graph is of size 2, consisting of just two vertices. If I choose, every edge in the graph is incident on, has at least one endpoint in this set S. And similarly for this graph, it is 3. Okay. So I hope the problem statement is clear. Okay, good. So let's go on to what do we do? How do we actually try to solve this? Okay, so keep this graph in mind, say, and for concreteness, let me label the vertices. So this is a 6 vertex graph down in the left corner that I'm using. Okay. So now let me go back to what we did with the theta function and things. I will try to formulate it as an optimization problem. Now, I may not get a easily solvable optimization problem, of course, but let me make a first shot of it. Yeah. So how do I do this? Okay. So given an input graph G, I make the following formulation. I pick one variable per vertex. Right. So there are n variables where unless stated, v will always be 1 to n. Okay. So I'll pick one variable per vertex. Okay. And these variables I will constrain to be either 0 or 1. That is, they will be indicator vectors of sets. Okay. So I'll constrain the domain of these variables. Unlike in the previous case where there was a continuous domain, you want to constrain the domain of each of these variables to be between 0 and 1, to be either 0 or 1. Okay. Subject to this, I'm going to optimize the quantity. So think of xi's as being the indicator vectors of the set that is chosen to be independent. Okay, of the independent set chosen. So I want to minimize summation I over v xi such that, well, all the xi's are 0, 1, right? But further, I want the xi's to be the indicator of an independent set, right? So how do I ensure that? Right? I'm going to put further constraints on this variable depending on the graph structure, that is the edges that are there. Notice that I should never choose two. I should never choose two vertices, both of which are okay. Sorry, it should be not an independent set, a vertex cover. Yeah. So for every edge in the graph, I should choose at least one endpoint. Okay. So how do I ensure that for every edge in the graph, I choose at least one endpoint? Okay, so this for vertex cover. Okay. So what I say is, well, xi's are 0 and 1. And what I want is for every edge, I should have xi plus xj should be greater than equal to 1. Okay. So notice that combined with the constraint, any feasible solution that satisfies these constraint will be the indicator vector of an independent set. Okay, why is that? So for instance, suppose I look at this graph, right? What would be the objective and the constraints that I write out? For this graph G over here, I would write out minimum x1 plus x2 plus so on until x6, subject to, and then what are the constraints I put? For every edge, I'll have to write a constraint. So I have 1, 2, 3, 4, 5, 6 edges. So for instance, I'll write x1 plus x2 is greater than equal to 1, x1 plus x6 is greater than equal to 1, x2 plus x5 is greater than equal to 1, and so on. So there are 6 constraints. I will write all of them for each edge. And then I'll write every xi is in 0, 1. Right. So for this particular graph here, here is the corresponding LP. If I manage to solve this by feeding it into a solver, that would be great. But I cannot expect to do that because this is not a linear program. The objective is linear. These constraints on the edges are linear, but this discreteness is the problem for us. Okay. So the fact that xi is constrained to be either 0 or 1, right? That makes it that ensures that it cannot be solved efficiently. Okay. So now, how do I fix this? Well, remember that this thing, the optimal of this. So let me write two properties of this formulation. So suppose I write z equal to this. Any solution, so let me be a bit more precise, any feasible solution to this problem is actually what is going to be an independent set in G. So it's the indicator vector. Oh, so I keep saying independent set. It's of a vertex cover in G. I'm sorry. We have spoken enough about independent sets. So it's indicator vector of a vertex cover in G. Why is that? Well, for every edge, at least one of the endpoints is 1. So if I just collect the vertices that have set to 1, then I will get a vertex cover in the graph. Okay. So all feasible solutions are there. And since I'm minimizing the size of the set that is chosen in the objective, summation xi will then denote the size of the set that is chosen. This implies the optimal solution will be a minimum vertex cover. Okay. So is this setup clear? Like what we're trying? So we have given an optimization formulation. And what I've argued is that the optimal value of this formulation is indeed equal to the minimum vertex cover in the graph. However, we can't expect to compute this efficiently. Okay, because of this discreteness constraint. The rest of it is almost a linear program. It says summation xi, which is linear, and xi plus xj greater than equal to 1, which is linear. Right? So what do we do next? Well, we relax it. Okay, we find a proxy for it that can be computed efficiently. And what is the proxy going to be? It's closely related to this formulation. And just like the theta function, it's going to be a formulation that can be solved efficiently. That is going to be a linear program. Okay. And this is it. Okay, so maybe I'll not write the algorithm first. Let me write what is called the relaxation first. So I'm going to minimize xi such that summation of xi such that every edge, so every edge, at least one endpoint is chosen. So it forms a vertex cover. But instead of the discrete constraint that xi is between 0 and 1, it lies in either 0 or 1, okay, I will make it into a continuous constraint, which then becomes a linear constraint. Right? Now, this is closely related to the previous one, right? Previous optimization. This is also an optimization formulation, okay? However, it's closely related to the previous one. That means I have expanded the domain out, right? For every I, in the previous formulation, I could only take 0 or 1. Okay, and that was giving me a minimum vertex cover in the graph, right? The value and the solution was a minimum vertex cover. Over here, since I've relaxed it, right, the domain has blown up, right? From just being 0, 1 discrete to the continuous interval 0, comma 1. What I've gained is that it is efficiently solvable because this is a linear program. The objective and the constraints are all linear functions, so they are efficiently solvable. But the answer need not be a LP, need not correspond to an independent set anymore, right? And why need not correspond to independent set anymore? So maybe the output of this, let me call it ZLP, okay? So the output when you solve it, that is you feed it into a solver, it gives you some answer X star, which is the optimal of this program. It need not be integral. Okay, if it was integral either 0 or 1, then I know that, the ones, these points where xi is equal to 1 should be the indicator vector of an independent set. But that is not true. Or in this case, where it need not be integral, and you can have xi's may be fractional. And once the xi's are fractional, how do I get an independent set out of this? Right? Because I no longer get. So suppose I get some values. Say the optimal solution x star on say the 6 vertex graph we see might look something like 0 0.2, 0 0.3, 0 0.47, 0 0.9, 0 0.6, something like this. Right? Nothing is stopping it from being like this. Now looking at this, it doesn't look like an independent set at all. It has fractional values sitting in it. So what do I do? And this is where I need another layer of an algorithm. Okay. So what do I know about this? I know that the value of this solution, summation xi star, because the domain has expanded, the objective value on the optimal solution of this continuous program should be smaller than, because it's a minimization and minimizing over a larger domain, is less than equal to the optimum. Okay, what do I mean by optimum here? The minimum vertex cover in the graph. right? And therefore, this is just saying that ZLP is less than equal to optimum, always, right? Because we expanded the domain. And our proxy for the optimum is going to be exactly this ZLP, okay? Instead of working with the optimum, which is difficult to compute, I'm going to work with ZLP, which is easy to compute, okay? This is like what the theta function was for the Shannon capacity. Okay, it's efficiently computable and it bounds the optimal solution from one side. But then the problem remains, okay, I found this, but then algorithmically, how do I extract out a independent, how do I extract out a vertex cover? So, so we'll do that next. And it's really simple. You know what? It's a natural thing that one should do for this particular problem. So suppose, so the algorithm is the following. I run this. So formulate this problem for a given input graph G, right? Feed the above into a solver. And you get a solution X star, which is optimal, but it's optimal for the LP. It's not the actual optimal solution. So I'll just write it. Solution. X star is equal to weight X star 1, so on, X star n. With value, maybe I call this ZLP star, which is summation Xi star, which is at most the optimum, where optimum is the size of the minimum vertex cover in the graph. Okay, so I get this value. Yeah, and I get this fractional solution. You know, I call it fractional because it may be fractional. And now I need to extract out an integral actual independent set from this. Now what do I
Sir,
do? Yeah, question.
so this problem will give us the size of minimum vertex cover or the vertex cover itself.
So good question. So the algorithm that I'll design will do both. Okay, it will attempt to get a vertex cover and also I will bound its size. Okay. The problem definition asked you to actually find a vertex cover of minimum size. Okay.
Oh,
Okay. So we'll do both. We'll actually give a subset of vertices. So the LP solver will give you a solution x1 to xn star, and the value will be at most the optimal. Okay. The summation xi star will be at most the optimal. Then I've got this value also when I feed it into the solver. If it gave me xi star, I can just sum it up. Get it. Good. So now what do I do next? I'm going to try to produce a vertex cover from this. So I consider the set, and this is where maybe some amount of cleverness comes in. Okay. Look at the LP. Look at the solution x1 to xn star. In the ideal solution, what should it have been, right? If I was in the independent set, then xi star should have been 1. I would have expected. But the optimal is not that, right? It's giving me something else. It's giving these fractional values. So what I think of is, well, okay, it's not 1 or it may not be 1 and 0 exactly, but if the value is large, maybe it should be in the independent set. Okay. So I take the set of vertices such that xi star is greater than equal to half.
excuse me, sir.
Yeah.
Sir,
Suppose.
this summation xi star
Mhm.
should be greater than equal to opt or less than equal to.
It's less than equal to opt, right? Because this is a minimization problem, right? So what was opt? Opt was exactly the same thing, but with xi restricted to 0 and 1. So if I expand this domain, right, I minimize over a larger set, the minimum that I get Z over here will be less than equal to opt.
Okay, sir. Thank you.
Right. So because I'm expanding the domain, this will be minimum drops further. Okay. But it's dropping because it's not really an independent set. The solver is giving some weird fractional values. Now it's our job to extract out something from it. Okay. So let me extract out the set where xi star is greater than equal to half. Okay. So if xi star is greater than equal to half, what is going to happen over here? Right? I claim that S is an independent set. Can someone tell me why S is an independent set in G? Sorry, I keep saying independent set. I'm really sorry. It should be vertex cover. Why is S a vertex cover? It's not the minimum vertex cover. Yeah. So I claim that it is a vertex cover in G. Well, the reason lies in the constraints. Consider any edge. Okay. If I pick any ij in E, I claim that at least one of the endpoints should have had a xi star value greater than half. Why? We know that xi star plus xj star is greater than equal to half, greater than equal to 1, right? Because the solution satisfied this constraint for all edges. And so the optimal solution did satisfy this constraint for all edges. We know that xi star plus xj star is greater than equal to 1. And what does that mean? That implies that at least one endpoint is selected. Why? Because we know this is greater than equal to 1, so one of them has to be greater than equal to half. If both were less than half, the sum could not be greater than equal to 1. Okay. So that tells me that S is a vertex cover. Now, how do I guarantee its size? I want S to be as small as possible. Like, why is S, why is the size of S small? Okay. So what I'm going to do is I'm going to consider summation I element of S, summation xi, or rather summation xi star. Now, I want to compare this in some way to the remaining. Right? So just give me a second. I'll just have some water and be back. Oh, this is my video. Yeah, good. Okay. So yeah, what I wrote here, let me just change this a bit. So what I want to do is bound the size of S as compared to the optimal. Now, how do I bound this? I look at the size of S and I say, what is this? I element of S 1. Okay. A trivial statement. I'm just summing 1 for every I in S. Okay. There's nothing great in this. Now I claim that this is less than equal to 2 times summation I in S xi star. So why is this true? This is because I only chose those vertices whose xi star value was greater than half. Right? So if xi star is greater than half, that means 2 times xi star is larger than 1. So this is true. And this thing is at most what? Well, now it's easy. I'm going to say that this is less than equal to 2 sum over all of xi star. And this is because xi star is greater than equal to 0. I've just added some more terms over here. Okay. But what is this? Recall that this was exactly the objective value of this relaxation, okay, of this LP formulation. And what do I know about that objective value? Its value is less than equal to the optimal vertex cover. Right? So what we have shown, if you see, this is the min vertex cover size. Okay. The size of the S that I output, first of all, S was a vertex cover and its size is less than 2 times the optimal. And what's the crucial step over here? The crucial step is comparing S not to optimal, which I don't know what it is, but comparing it to ZLP somehow, okay, which is efficiently computable. And I know how ZLP compares to the optimal. Okay, so ZLP is a proxy for the optimal, and using that, I can do very interesting things. So that's the idea. So it's at least the philosophy clear. Some of these small calculations, I hope it's mostly clear. But if it's not clear, that's fine. But I hope at least the philosophy is clear what we are going for. Okay. So as we see other problems in this field, the techniques become more and more complicated. You either need to formulate a relaxation um, of this form that is not so straightforward, or even if the relaxation is straightforward, maybe the rounding algorithm for it, the one that produces the solution from the fractional solution, will not be very straight. Okay. So one of these two will typically be hard. So this is our first algorithm. I hope it gives you a flavor of this. Now we'll try to do the same for something called the max cut problem. I'll not do a complete proof because of lack of time, but I will show you how the relaxation is formulated. It will give a SDP relaxation, not a linear programming relaxation, but a semi-definite programming relaxation, like the theta function was. And I will just give a geometric idea because once you have a semi-definite program, you have vectors and stuff, a geometric idea of what the rounding procedure does without looking at the analysis. Okay. Good. So we saw one minimization problem, the vertex cover problem. Let's consider the maximum cut problem. Okay. What does the maximum cut problem ask you to do? You're given an input graph G, right? Um, which is consists of course, V and E. I will again identify V as 1 to 1. Right? And the objective is to find a partition of the vertex set that maximizes the number of edges going across the cut. Okay. So partition consists of two parts, S and S complement into two parts. So it's a partition into two parts. There are generalizations into partitioning into K parts, but that becomes more complicated. Okay. Uh, we'll just look at the two-part version for that. Okay. So for instance, for this particular graph, you have S and you have S complement. And if you see the bold edges here are the ones that go across the cut. So the value of this particular cut Yes, you have 1, 2, 3, and 4 edges going across, so the value is 4. Okay. And you want to find a cut that maximizes this value. So maybe another example, which may be somewhat illustrative, is this. Yeah. So this is a graph. Can someone tell me this has 4, 5, 6 edges? Can someone tell me what is the maximum cut value in this graph? Well, maybe you can work it out. I guess. Uh,
I mean, the two
mhm.
sides of a square, if you take those two, 2 and 4, if you take in one set,
Yeah.
and the remaining in other sets.
Right. So
So,
now if you look at this, you will see that every edge is cut, right? So you will see that this cut, so S is the darkened vertices and the others. So you'll see that every edge is cut because this goes across, this goes across this. Okay. So the max cut value can be as much as all the edges in the graph. Okay. In fact, for bipartite graphs, clearly it should be the maximum cut value is 1. This is a non-bipartite graph, but still it is not 1. It is equal to the number of edges. Okay. You can cut all the edges using 2 part of the vertices. Okay. Now, if you have seen the min cut problem before, you will know that that can be computed in polynomial time efficiently using a flow algorithm or other. Okay. Or at least it will have been mentioned. But the maximum cut problem is NP hard to find exactly. Okay, to finding the maximum cut in an input graph tree is NP hard. And the best we knew for a long time was a half approximation. And actually, I'll outline it in the next one. It's kind of trivial. Okay. And to go beyond this half barrier, that is to produce a cut which is provably more than half of the optimum, it was done by Gomans and Williamson first, who in 1994 gave an algorithm that guarantees to give a cut which is at least 0.878 of the optimum. Okay, and this was the first paper that introduced the SDP, introduced SDPs for designing algorithm. And since then, there has been a lot of work and a lot of problems for which SDPs have given really good algorithms. Okay, so here's a first observation. I claim that the optimal, that is a cut, there exists a partition which cuts at least half of the edges overall. Okay, for any graph. Opt is the max cut value. So what I'm saying is there exists a partition that will cut at least half the edges always in your graph. Does anyone know how one can show this? So you can show this via a randomized argument. Okay, I'll just do it here. It's not very important to what follows, but it's neat enough that it will fit in 2 or 3 lines, and it's useful to kind of keep in mind, what the range of parameters that we're dealing. Okay. So notice that again in max cut, I need to output a set of vertices S effectively because I output a set of vertices, it and its complement is implicitly the partition, and the edges going out of S into S complement will be contributing to the objective value, right? So how do I pick this S? Let me choose S randomly. So I do this irrespective of the input graph. That's why it's kind of a trivial algorithm. For each I in the vertex set, choose I to be in S. with probability half and do this independently. So for every vertex I, you toss a fair coin, and if it turns up heads, you include it in the set S. Yeah. So now the claim is that what I'm going to analyze now is the expected number of edges cut. So notice that because this is a random process, the set S that I generate out of it is random, and therefore the number of edges going across the cut is going to be random. And I will analyze the expected value of this. So how do I analyze the expected value of this? I'll just use linearity of expectation. Okay. So define the variables xij. If I and j lie on opposite sides of the cut, that is I is in S, j is in S complement or otherwise. Sorry, xij should be 1 if it lies on opposite sides of the cut, and 0 if they lie on the same side. Okay, it's 1 if they lie on opposite sides and 0 if it lies on the same side of the cut. And what I'm interested in, the expected value of the edges going between S and S complement is nothing but expected value of edges, sum over the edges of xij, which is an indicator random variable. But now, notice that despite the variables being dependent, I can use linearity of expectation and say that this holds. But then what is the expected value of xij? It is a probability that xij is 1. So if I pick a single I and j, sorry. Right, and this is the random variable xij. What is the probability that xij turns out to be 1? Right, I'm tossing a fair coin at I and j, right? So xij turns out to be 1 when xi is 1 and when I turns out to be heads, the coin toss, and j turns out to be tails or vice versa. Right? That is I is in S and j is not in S, or I is not in S and j is in S. What is the probability of this happening? It is exactly half, right? And so the sum is half times the size of the edge set. And because this is half times the size of the edge set, I know that there should be some set S that attains this value because the expected value of the number of edges going across is at least half times size of it. Okay. So there exists a set which makes half times size. And therefore, what is a trivial half approximation algorithm? Right? I claim that I could just output. Okay, yeah, so this is a randomized algorithm now, and that I can give for this problem, okay, which is basically the following. So I'm not formally defined what a randomized algorithm is, but I hope to do it through this example. A randomized algorithm is the following. Choose an S as above. Output S comma S complement. We know that the expected performance of the algorithm, the number of edges going across the SS complement cut, is greater than equal to half times the size of edges itself. And the number of edges is a trivial proxy for the max cut in the graph, right? You cannot have a max cut larger than size of edges, so it's at least half times the optimal. Oops. Okay, so this is a randomized algorithm for the problem, and it outputs something. It outputs an answer whose expected value is at least half times the optimum. Okay, notice that in the previous case, or when I defined approximation algorithms, I had not mentioned anything about randomization. But typically what happens is that if you have a randomized algorithm for a problem, you can make it deterministic with some effort. And in this case also, the same algorithm can be made deterministic. You can output deterministically a set S. Okay, so typically as computer scientists, when you're looking at this, you give a randomized algorithm first, and then afterwards later try to make it deterministic. In many cases of applications, the randomized algorithm will be enough, okay, to solve the problem, or the guarantee given by the randomized algorithm will be sufficient for applications. Okay. So any questions about this randomized algorithm and how it has worked? Okay, so I think I have around half an hour, which will be just about right for going over going over the Gomans-Williamson algorithm. Okay, good. Now, what we saw was approximation formulation for MaxCut that did not really use a optimization formulation yet. So I could attempt to do what I did with vertex cover, right? I could try to write a formulation for MaxCut, an optimization formulation where the constraints and the objective are all linear, and then try to solve it. However, it turns out that linear formulations do not work very well for MaxCut. Okay, I cannot go into detail as to why they do not work, but we know that, typical linear formulations for MaxCut don't really give good answers for approximation. Okay, so let's start from the next simpler function after linear. Let's start with a quadratic formulation. Now you may be suspecting that, okay, if I have a quadratic formulation, how do I ever get into one of either a LP or a SDP, right? We'll do that. We'll actually manage to get a relaxation into a SDP, even though the final SDP constraints are all linear in its variables. We'll start with a quadratic formulation for MaxCut. Sorry. Yeah. So what is my quadratic formulation going to look like? That is, either my objective or the constraints will have quadratic functions in them, degree 2 functions in the variables. So this is possibly going to come a little bit out of the blue, but I'm going to say my variables. Well, I still need to find a set S, right? So my variables will be what is expected. They'll have one variable per vertex to indicate whether that set S is chosen or not. Okay. But I'm going to tweak the domain of these variables for some reason. It's not really required, but it makes the formulation very clean. Okay. I'm going to make these variables lie not be either 0 or 1, but I'm going to make it to be -1 or 1. Okay, where xi equal to 1 means I element of S, and xi equal to -1 means I not element of S. Okay, it could be the opposite also, doesn't really matter. So this is a constraint. Okay, you have n variables, n scalar variables, each set to 1 or -1. What is my objective? Right? Maybe I'll give myself a bit more space for the objective. I'll write this here. Okay, so I'm doing a max cut. So the formulation is a maximization problem. That's great. What do I do next? Well, I'm going to write down the objective as the following. I need to find out which edges are cut, right? And every edge that is cut should contribute 1 to the objective value, so that when I sum over all the edges, I get 1. So I'm going to write this out and you can verify that this indeed does measure it. Okay. I claim that this objective function, subject to xi being -1 or 1, exactly captures the max cut value in the graph. Yeah, well, I don't need anything more. So, okay. Why is that? Let's verify this. Okay. So consider an edge ij. So I claim that the optimum of this formulation is exactly the max cut value of G. Okay, that is OPT as I've defined is exactly equal to this. Why is this true? Well, pick an edge ij. Right. All I need to show is that for any feasible solution, xi, x1 to xn to this problem, right, the objective exactly captures for that feasible solution the number of edges going across the cut. So if I pick ij, the objective 1 minus xi xj, the term corresponding to this edge in the objective, by 2 is equal to 1 exactly when xi is not equal to xj, right? So when xi is not equal to xj, that means xi is 1 and xj is -1, or xj is 1 and xi is equal to -1. When that happens, the object, the numerator is 2, the denominator is 2. So you get exactly 1. Okay. However, when xi equal to xj, this is 0. So any feasible solution corresponds to a set S, and the objective value on that feasible solution corresponds to the max cut value. Okay. So I hope this is clear. This is a quadratic formulation. Okay, first of all, because the objective is quadratic in the variables xi and xj. And secondly, as compared to our min vertex cover formulation, my xi is lying -1 and 1 and not 0, 1. So they're not directly indicator vectors. There's some shifted version, but it tells me what the set is. Okay. And again, like in that version, because of this constraint, forget the quadratic constraint for now, but this discrete constraints prevents me from solving this properly. Okay. But then what I could do one thing, right? Instead of putting xi in -1 and 1, right? I could just write a quadratic constraint over here, which is equivalent. I could say that xi squared is equal to 1, which basically implies xi is either 1 or -1. Right? So I have a quadratic function, quadratic constraints. Okay, so now it looks a bit more linear, right? Similarly, if I wanted to put a quadratic constraint for xi being in 0 or 1, I could have put it as xi square equal to xi. So quadratic formulation will capture. So I can put xi squared equal to 1, but again, the quadratic functions are too much for being efficiently solvable. It kind of stops at linear. At least the domain should be linear. So now what do? I need to relax this. Okay. I'm going to relax the quadratic form to a semi-definite program. Okay. And I'm going to do it through vectors. Okay, and that's the passage into the SDP world. So here's my quadratic program, which is basically it has integer constraint because xi squared equal to 1 is basically an integral constraint. Okay. So the first step in relaxing it to SDP, and it's basically the only step, is to replace these variables by vectors. Okay. Replace the scalar variables xi by vectors. So for every xi, I'm going to keep a vector vi. You may think, what am I doing? I mean, I want something that is efficiently solvable. This is not efficiently solvable. If I replace scalars by vectors, it seems to get more complex. But hold on for a second. Okay. I'm going to replace the usual scalar product here, xi times xj, by a dot product. So let me use, yeah, I might as well use, because I've used u throughout. And the square equal to 1, I'm going to replace by what? I'm going to replace by the fact that these are unit vectors. Okay. So instead of xi, I'm putting ui, and ui is in some n-dimensional space. Okay. So how have I gained by going from this scalars, which seem nice and handleable, to vectors here? So if you recall, our SDPs actually were vectors. We had written many of these SDPs, couple of SDPs for the theta function in terms of vectors. Why are vectors more efficiently solvable than simple scalars? If I can solve vectors, can't I solve scalars? No. The reason is that vectors are continuous variables. So the sets that you're working on, the set of feasible solution lies on the sphere, which is kind of more continuous, right? Whereas these are discrete points in this world. And typically optimization over continuous spaces is easier. Okay. It's more efficient. And so what am I going to do now is going to look at this. And if you want it in the usual SDP form, entries of a matrix and stuff, I'll just look at the gram matrix of the vectors. That is Yij is equal to Ui transpose Uj. Right? This is what it is. And once I define this, you'll notice that everything becomes linear here. The SDP, so let me call this as the SDP is basically this maximization again, a linear constraint in the y's, but the only constraint I have, y should be a gram matrix. But if you remember the definition of positive semidefiniteness, that is equivalent to saying that y is positive semidefinite. Right? So this is the semidefinite programming for MaxCut. It is a relaxation because every feasible scalar solution is also a vector solution. Okay, every feasible scalar solution to the original problem is also a vector solution, but now we have expanded the space furthermore, right? And since I've expanded the space furthermore, the maximum increases. Okay, so if this is the value of the SDP program, let me call it ZSDP, is the optimum here, then what I know is that ZSDP is greater than equal to max cut of G. Okay, because my domain of potential solutions has expanded out to a larger domain than just the integer solutions that were here in the scalar case. Okay, for instance, you could have taken all of these vectors to be one-dimensional, and those solutions, the xi square equal to 1, are still present over there. Okay, but now I've expanded the space further. For some reason, that makes it easier to optimize over. So this is efficiently computable now, ZSDP. And now I'm going to use this for my analysis. Okay. So what is my algorithm going to be? Here is my vector. I have written Sn minus 1. Here's the SDP, right? Sn minus 1 is just the set norm ui squared equal to 1. It's the surface of the unit sphere. Okay. So suppose I call this SDP1. Okay. It's equivalent to the other SDP. Whether I write it in vector form or write it in the Yij form, it's basically the same thing. Right? It's the same optimization problem. The vector form is easier to visualize geometrically, so we'll go with that. Okay. So the algorithm is the following. Once you get an input graph G, write the above relaxation. And feed it into a solver. So what does the solver spit out? Right? It will spit out a close to optimal solution. Let us just assume it will spit out an optimal solution to the SDP. Okay. And the solution takes the form of these vectors, these n vectors on the surface of the unit sphere arranged in some n-dimensional space. It is some geometric representation of the graph. And the value of this value means the objective function. Okay. Equal to, let me say, ZSTP. And we know that this objective function value is greater than equal to the optimum max cut. So I'll just write it as max cut. The only thing is these vectors are kind of just spread out in space. Right? They do not have any fixed, like they do not take this -1 values or something. It's some n-dimensional space. They are all spread out on the surface of a unit sphere. Now, finally, what I want to output about the graph, I want to output a set S, subset S of vertices that defines the partition. So intuitively, what I would expect this. Right? What do I intuitively expect about the solution? So I expect, so notice what this STP is trying to do, right? UI transpose UJ. So if all of these are on the unit sphere, right? UI transpose UJ is basically, because these are unit, so UI transpose UJ is the cosine of the angle between UI and UJ, right? So it's trying to maximize 1 minus cosine of the angle. Okay, and cosine is kind of decreasing. So what it's trying to do is for every edge, it's trying to push the vectors on the sphere further apart as much as possible. Okay. And it's trying to do this as best as possible. How far can I push the edges apart so that the total over the sum of the edges is as high as possible. So what you would expect is that if there's an edge between I and j, okay, that was supposed to be cut, then it would have tried to push this. The SDP would have kept these two vectors as far apart as possible on the top of the unit sphere. So it will have a large angle between them. Okay, so that is what I would expect. Just give me a second while I check my laptop charger. Just give me a second. Okay. So if ij is an edge, I was saying that it would expect that you have a large angle between, right? Especially if ij is supposed to be in the maximum cut. Ideally, what the solution should look like, I would expect, at least intuitively, is that, well, this is my unit sphere. Everything with S lies one side, kind of. and it's far from S complement, which lies here, right? So I would expect something like this, but the SDB can do some weird stuff, just like in the vertex cover, it gives some fractional values like 0.45, 0.6, 0.9. It may do some weird stuff because I'm in n-dimensional space and I cannot expect such a clear picture of, getting SMS complement. But then I'm going to use this intuition to next design the next step of the algorithm, which will actually find me a solution. So here again, I'm going to give a randomized algorithm, and it's a rounding algorithm because it takes these fractional vector values and gives me a honest to God set, okay, of vertices. So how do I work on that? So the idea is the following, that you have vectors on the top of units on this unit sphere, right? And the edges are kind of far apart, right? But the edges are all over the place. It's not like they're all well aligned in some nice way that I can exploit. It was not as simple as the vertex curve problem where I could just say that, okay, beyond this threshold is fine and below this threshold is not in the set. So I cannot say such a clean thing about solutions, these solution vectors in n-dimensional space, but I will use a randomized procedure. Since things that have an edge are supposed to be far apart, I'm just going to randomly cut the sphere. Okay, so this is an n-dimensional sphere, but you can imagine a cut as a hyperplane cut. Okay, that's what is shown here. And everything on one side of the hyperplane, I'm going to put as S, and everything on the other side of the hyperplane is going to be S complement. Okay, so that is the rounding algorithm. Okay, how do you describe this? Let me put this first, write the informal version. Choose a random hyperplane through the origin. Oops. Okay, that cuts the sphere, sorry. And you have points on one side. Pick the points on any one side. The vectors that lie on any one side, the corresponding vertices are going to form S. No, I should not say point, I should say vectors. I don't care which side you choose because finally outputting a partition S and S complement, either one is S. Okay. So is the algorithm clear? I fed it into a solver, do a random cut, and that's the algorithm. So how do I choose this random hyperplane? You can choose a random hyperplane in n-dimensional space by specifying its normal vector, right? Let me call this normal vector P. So I choose a random P, okay? And that's the one that is my normal vector. It's going to define the hyperplane. And then how am I going to define which points are S? These are the points where P transpose Ui is greater than 0. Okay, and other side is J such that P transpose Uj is less than equal to 0. Okay, equal to 0 is a measure 0 event. So, I mean, you just forget that. Okay. So this is S and this is S complement. Okay, this is clearly a valid cut. It's a partition of the vertices. And what remains to show is that this cuts many edges. Okay. But like in the previous randomized algorithm for max cut, I'm not going to actually bound the edges because that's a random function, right? So how do I bound it, right? I'm going to bound, it's a random depending on the random hyperplane that is chosen. Choose one hyperplane, you get one cut. Choose another hyperplane, you get another cut. But since I've chosen a random one, I'm going to bound the expected value of this quantity. Okay. And what Gomans and Williamson did is they came up with this. They used the STP, came up with this algorithm, and showed that this thing is at least 0.878 times the actual max cut. Okay, it's a continued fraction. I will tell you what that is in a moment before we stop. Okay. So any questions about the algorithm or how it's working? I mean, it's quite a non-trivial or out of the blue algorithm. Typically, you don't expect algorithms to take this form. Uh, but it's a very clever and it's a very nice algorithm that has found many further uses in extension. Good. Okay, so let me go ahead and see how do you bound the number of edges. It's going to be very similar to what we did for the randomized max cut before that gave the half approximation, right? I'm just going to take one edge at a time, right, and use linearity of expectation. And that's the beauty of this. It makes it really simple. Okay, pick any edge ij. And let xij equal to 1. It's an undirected edge. Lie on opposite sides. And we'll try to analyze what is the value of this, what is the expected value. Right? Now, how do I analyze this? So I'm just doing one edge at a time. So the expected value of size of SS complement is going to be like before. I'm skipping one step here. Okay. How do I bound the expected value of xij? Okay. It's by looking at the following problem. So I have I and j, just like we did in the randomized, right? I and j. Now I was tossing coins in that case. In this case, I have two vectors on the unit sphere. This is ui and this is uj. What's the probability that I separate them? Well, it turns out if I pick a random hyperplane, it's like picking a random line in this two-dimensional space spanned by these, right? And what's the probability of cutting them or putting them on opposite sides? If I pick a random cut of this circle, right? It's proportional to the angle between them. So if theta is the angle between them, it's proportional to that. And what is theta? Theta is cos inverse. So probability of opposite sides. Xij is equal to 1, ui transpose uj divided by, well, this slide, it's not 2 pi because, the theta could be here also. Depends on where the normal vector falls. Pi pi. Okay, this is just theta. Okay, and there's good reason that this falls. Okay, so probability that xij equal to cos uij. So maybe I'll call this as theta ij, the angle between I and j. This is theta ij. And now I need to relate this back to my original one. And Gomans and Williamson, just this is what I had told, that you get cos inverse of ui uj for any two vectors. I'll skip this part for lack of time. So if alpha is the angle, I get alpha divided by pi. Right. And this was the probability of separating I and j if z was theta ij. And the claim is that this is at least this weird number times 1 minus z over 2. Okay. So set z equal to ui transpose uj. I'll just take a minute more. So probability that xij equal to 1, 0.87856 times 1 minus ui transpose uj by 2. And this implies that the expected number of edges cut. So this is a lemma that just requires calculation. You take the maximum over all z. Summation expected value ij and e of xij, and this is greater than equal to 0.87856 times summation 1 minus ui transpose uj by 2. But what is this? This is exactly the objective value, right? And the STP value is at least the optimum max cut. Okay, so I've rushed through this last calculation, but I hope at least the algorithm is clear and the way of analyzing is in principle similar to the previous one, just that because you're dealing with vectors, you will be a bit more careful and you get a better approximation factor. So let me go on with some closing remarks. Okay, so this power, how powerful are SDPs in approximation algorithms for these problems is a topic of very active research. Okay, even now. We don't understand the power of these completely, but a lot of progress has been made in understanding computationally what they can do. And this weird number of 0.87856, well, it's kind of believed to be the best that you can do. For some exact same number turns up. And for other problems, STPs have been used, and we do not know which are, which are optimal, and how much more are there more clever algorithms that can use on similar lines that can give better approximation ratios. And one thing I want to say, all of this, of course, you see the parallels back to Lovasz's bound, right? There was this relaxation, which was efficiently computable, and you could also analyze more easily. The same thing is with STPs also, right? Because that was effectively an STP, just that this came 20 years roughly later after Lovasz's bound, and the connection was discovered that you can actually use STPs for these kind of approximation algorithm tasks. Okay. So I'll stop here. I think I'm a couple of minutes over time, but if anyone wants to ask questions, I'm happy to stick around and answer them. Stop at this.
Okay. There is no question, then I stop recording first.